Okay, so what I'm going to speak about today is to do with the intuition of intuitions that have to do with the model. Oh yeah, so the model. So let me first make sure we understand what I mean by when I speak about models. So let me see if I have access here, or it's okay. I do. So a model is both a theoretical and a practical concept that we need to understand. We need to understand how they relate to each other. So let me start this here. So from a theoretical point of view, a model is just a set of possible functions that we're trying to learn. Okay, so it's a set F of functions, say from just as an example, from a Rn to a R. So this is a model. It could be a finite set. It could be an infinite set. But the point is that the model captures our intuition or knowledge about the world, and it biases what we're looking for as a model. So if the model has functions and doesn't have other functions, that would mean we're going to search only for the functions in the model, not functions outside. Now, this seems to be a very, abstract notion, abstract concept, but it's not really. Because if you think about a neural network, for instance, it's a model implicitly because you have the weights on the edges and you have other parameters that determine the behavior of the neurons, like thresholds. So, so basically, the model is the set of all functions that we could choose that will correspond to a specific choice, weights on the edges, and so on. So given a neural network, I implicitly define the theoretical notion of a model, or giving a logistic regression, giving an SVM, giving any machine learning technique that we're using implicitly biases the world or define a model that we are choosing for. And we're not searching, we're not looking for an answer for a specific a machine learning function that is not in the model. That's the bias that we introduce when we choose a model. Is that point clear, and do you have any questions about it?
I think I follow.
Great. Okay. So So the next thing, once you understand that, the next thing is the fact that models can be more complex or less complex. Intuitively, models that are more complex have more options, more possible functions that we consider in research for the best answer in that domain. Okay, so just to give an example, if these are the points of my data sets, then we would say that the tendency of this data set is not linear, okay? Because it goes like this, right? So maybe it's a quadratic tendency, not a linear tendency. So essentially, by saying that we're going to model this data set using a linear equation or using a quadratic equation, we're saying something about our belief system about the world and about this data set. And the linear one will be more simple than the quadratic one, because any linear model is also a quadratic model with a coefficient 0. So if you look at a linear model like this, y equals so this is a linear model, but it's, you know, it's implicitly a quadratic model of the form well, 0 times x squared. Okay. So it's, you know, a linear model is a quadratic. When we're only limiting ourselves, when our model is linear, then we'll only be choosing A and B. When we go to a quadratic model, we'll be choosing A, B, and C. It will be a bigger set of possible models. And so it's more complex. And the chance is that when you go too complex, you start picking up noise, and you may end up with something like this that will not predict the data well. And that's called overfitting. Is that clear up to now?
Yep, makes sense to me.
Great. So basically what I want to show now is a simple example in which in some cases you may increase the complexity, because this is one of the things that's not intuitive sometimes. You can increase the complexity, but still you don't run into the issue of picking up the noise, so to speak. So let me show you a little demo. So I'm running this code, and let's look at the result first, and then I'll explain it. So I started with I'm inserting some. What I have is some relation of degree 2 with 2 variables, a polynomial of degree 2 with 2 variables. I'll show it in concretely in the code. Then what I'm doing is I'm trying to match it with so my model is a polynomial of degree 1, and that's the error I get. Now, if I try to do it with a polynomial of degree 2, because I've inserted a polynomial of degree 2, naturally, I get a much better estimation. Now, if you look at the coefficient, you see that most of them are, more or less 0, and there's one of them that is more or less 1. So basically, it picks up the exact polynomial despite the noise. Now, what's going to happen when I keep on going? So say I go and I try to do a polynomial of degree 3. Okay, so the polynomial of degree 3 is gives me a much less a higher error basically, and you can see here in the coefficients that the real relation is not picked up. The coefficients are given to all the variables. This is x, this is y, this is x times y, this is and so on. X to the power of 2, y to the power of 2, x to the power of 3, y to the power of 3. So, and you can see that the average error doesn't change when I take a fresh sample, but it's well, it doesn't change significantly, but basically the real relation is not picked up. Now, if I go to the polynomial here, you would see that the polynomial I'm picking has this random error. Now let's try and basically remove the error altogether. So I'll remove the error in the polynomial. So this is a very simple quadratic polynomial. I remove the error altogether, so there's no error now. And now I ran it again. Anything we notice? Well, one thing is that here it it picked up the relation, but for degree 3, it's still not picking up the relation, which is what we expect. So you see that basically, regardless of whether because the relation is very clear, regardless of our intervention in terms of noise, and you can play with it. It's in the link. You would get a situation in which a polynomial of degree 2 will be picked up, and will do a good job on generalization on the first sample. But if you increase the complexity, you lose it. You don't have the relation. So you see, there's the message is that there's kind of a good bias you need to look for. So it's very important. The bottom line here in this one is, it's very important to be able to choose the right bias, right model for the problem. If you if you go too low or too high, you'll be in troubles. Any questions or comments?
And just to make sure that I understand correctly, the error is the error when we use when it's a simple polynomial with just one coefficient, the error is smaller, right? Than when you choose the four coefficients together. Is that correct? Do I see correctly? If you compare once you remove the noise, so what is printing on the right? It is the current error is 2.32, right? When the degree was 2.
Yes.
And when the degree was 4, the error was a bit higher on the first sample, right?
The degree is 3. So when the degree is 3, the error is well, it should be 3 here as well. Okay, but the error is you know the error and look at the coefficients for a minute.
Yeah, I see the issue with the coefficient that it didn't manage to capture the relationship.
Exactly.
But I'm asking, yeah, but even if it is not capturing the relationship, it still should have a lower error than choosing the coefficient 0 for the parameter, right?
It has a higher error than the error here, right? That's what you should see. It makes sense. You see, it's 2.32.
It's not getting the optimal solution?
What?
It's not getting the optimal solution? Because even as you said in the beginning, for the degree 3, it is still a valid solution if the coefficient is 0. It could be exactly the same solution, right? With just 0 for the third coefficient.
Oh, it could be, but the point is that it doesn't pick it. That's the point. It has the right solution in the model, but because I see your question. It has the right solution because it could, as I said before, it could be a 0, right?
Right.
But,
yeah.
Yeah, but because I increased the search space, I confused it. It doesn't pick it up.
So it's not converting to the optimal solution, but yeah.
That's exactly the interesting point. You got it now.
Yeah.
Okay? Yeah. So it's not enough to have the right solution in the space. You need to choose a space that makes sense in some way. That's the intuition I want you to get. Makes more sense now?
Yeah.
Great. Okay. So thank you very much for joining, and we'll do it again next week.
Thanks, Eitan.
Thank you very much, Eitan.
Thank you.
Thank you very much.
Bye-bye.